Hi, this is Aves from RIS. We are currently discussing Unit 13, which is Electrostatics, and we are going to continue our tutorials. This is second tutorial in the series. We're going to start with topic 13.1, but we're going to start with the self-assessment, which I had explained that we're going to discuss in the next lecture. So here it is. The self-assessment states that, do you think amount of positive charge on the glass rod after rubbing with silk cloth will be equal to the amount of negative charge on the silk? Explain. Now let's think of this. We were discussing in the last lecture of electrostatics, right, that if we take a rod, a plastic rod, right, and we rub it with a cloth, and due to friction of these objects, the plastic rod becomes negatively charged, right? Now we have another case where we have a glass rod. This is let's say plastic, right, and we rub it with a silk cloth. We rub it around, right, and what we get is, like, this is a glass rod, so this gets positively charged, right? Now we took neutral particles of paper, right, pieces of paper, crumbles of paper. Why paper? Because paper is very light, and especially when you tear it down to a very small piece, it becomes very light, and it's very easily attracted, or can be moved or lifted even by a little blow of air. So I think that is the very reason we use these small pieces of paper. You can use plastic wrapping as well. That gives you a much better fun, because it's even lighter than paper and gives you a more strong force of attraction feel when you're trying to look at it, when you're trying to observe how this is happening, right? So we experience that this is going to get attracted by both of these poles, whether it's positive or negative. Why? Because these are neutral, right? So neutral particles or objects are going to get attracted to surfaces which are charged, and I discussed that charge is energy, right? Energy which we deliver due to friction in this case. So this is the case where we're using friction to induce charges on two surfaces which are different materials. One is plastic, the other is glass. So plastic gets negatively charged because electrons jump from the fabric onto plastic, and when we're talking about glass, we see that the electrons on the surface, which are just jumping around on the surface of glass, not as a free current but as tiny little particles, they would jump into the cloth and leaving the surface of the cloth being positively charged, because loss of negative charge causes positive charge, and the gain of negative charge is resulting in negative charges, right? Considering that everything is neutral in the beginning. So the question is whether the cloth that we're using in this point, which is silk over here, and let's consider this fabric, any fabric, because plastic works with most of the things. Even with silk, it's going to get usually get negatively charged. So when we're talking about silk, if this is getting positive, the self-assessment is asking whether this would have equal amount of charges, and I just explained the fact that the electrons are jumping from here, right? The electrons which you've studied in chemistry, they jump from this surface onto the silk on this fabric. It's going to jump over here, right? So the electrons are over here. Yes, the answer is very simple. Yes, the amount of charge will be equal on silk, yet being oppositely charged. Yes, so this is the explanation, that the amount of charge will be equal on silk, yet being oppositely charged. Why? because obviously if something is lost, let's say this is a neutral atom. I'm going to draw an atom, a very simple atom, which is a hydrogen atom. If I take this electron away, right, I remove this, remove electron, what you get? A proton, right? And if I'm adding an electron, right, if I add an electron into an atom, let's draw it separately so that you don't get confused. Let's say this is an atom which is already neutral. This was neutral, right? Neutral. And again we're talking about a neutral atom, right? If I add another electron to this, adding electron, right? So now there are going to be two, which is unstable. Why? Because a hydrogen atom is supposed to have one positive and one negative electron. And why? Because neutral means equal positive and negative charges, right? That number of positive is equal to number of negative charges. This is what neutral is all about, right? This is what we call as neutral. The number of positive is supposed to be equal to number of negative. I think it's a little blurred. There you go, right? The number of positive is equal to number of negative charges. This is what neutral particles or neutral objects are supposed to be in sciences, right? So if we add an electron to a neutral particle or a neutral atom, it becomes negatively charged, right? This is what we also consider as a negative ion, right? Since this is an atom, over here we have a neutral atom which has lost an electron, so there is only left a single proton, but we call that proton as a positive ion, right? So moving on to the second assessment. So yes, explanation, we have explained that how these particles are equal. I've explained the whole fact. So this whole description was the understanding of self-assessment 1. Now moving on to the second. What would happen if a neutral glass rod is brought near a positively charged glass rod? Okay, now this is fun. We want to understand what a charged surface can do to a neutral surface, right? What will happen? Let's see. Consider we have one glass rod, right, which is positively charged on the surface, right, and we bring around another glass rod which is neutral. It does not have any charge at the moment. We bring it close. What happens? Consider it this way. If I have one hydrogen atom and I bring around closer to it another hydrogen atom, right, what will happen? We would find that, and especially let's consider that this is not a hydrogen atom. We will bring something bigger to see the effect in a much more powerful way. Consider this way, that we have just a proton, a bunch of protons, not just 1, 2, 3, but lots of protons, and they're packed up together like a gang, and they're moving together for some reason. Let's say this is an object which is just filled up of protons. Now this is a lot of positive energy. What is going to happen? We do know same poles, they repel each other, right? So what will happen? It would push the proton away, but it will pull the electron. Why? Because electron is negatively charged, while proton being positively charged will get repelled, right? And this would get pulled. Right? Now this is what we call as induction of charge. This is what induction is. We have induced it. We have not physically touched anything, yet we see a very dramatic physical change. What will happen? This atom is actually going to bend around, right? Now I'm going to redraw this on top because I have lack of space at the moment, because I need to make it more clarified. Now we have these positive charges, like lots of them. So what happens? The whole atom is going to get bent, with electron trying to revolve here while the proton trying to run somewhere else. This is called a dipole. That means two poles, one positive pole and the other one being negative pole, right? So this is means di means two poles, dipoles, right? So this is what induction looks like. This is the end result, right? So this is what induction is. When you bring a very strong positive charge and bring it around to the other one, a neutral particle. Over here we had a neutral atom of hydrogen. We brought an object which was very much heavily positively charged. It only had positive charges in it, no negative charges. Let's consider, although this is not that easily possible in science, in real life, but we're considering the fact that we have an ideal body which is just positively charged. It's an ideal case. So when we bring it close to a neutral particle, we see that the positive center has moved away, it got pushed away because there is repulsion, and for electron, which is oppositely charged, is going to get attracted. There is attraction, and hence two poles will get generated, positive and negative end. Now this is, since this is not an ion, the atom is not broken, we call this as partial negative and partial positive. This symbol which I have drawn, this symbol, right, this is called sigma, and this actually represents, for this kind of working, when you're talking about dipoles, this sigma symbol is representing partial, right, something which is not complete. So this sigma is usually used in physics for partial when you're talking about charged particles, and hence we have sigma negative over here and sigma positive end over here. That means partially negative area, partially positive area. So this is charge induction. And obviously if there's another neutral atom at let's say at this side, where this dipole is written, if I bring a neutral particle here, obviously this partial positive is going to also create another dipole in sequence, right? Let's draw that. Imagine if I bring another neutral particle, so this will happen to the other one. Not as strong as this one, a weaker induction, but still in real case this is going to be weak, but in an ideal case this is supposed to be equal. I actually try to incorporate more of the practicality as well along with physics. So very less ideal cases I would like to discuss unless it's part of the deal. Currently, since we're doing tutorials, so I think we can incorporate much of the actual science around it. So we are talking about dipoles. So this is induced, this is also induced, right? These dotted lines are representing forces of induction, which in times we also see in hydrogen bonding and van der Waals forces. They are all the same similar phenomenon, electrostatic induction, where we see it happening. Especially a very strong function of electrostatic force can be found in what we call as ionic compounds, right? If you look at ionic compounds, you will find that ionic compounds are made up of electrostatic particles, and the force of attraction or repulsion is so massive that ionic compounds are usually known for high melting points, at times even higher than those of metals, which are like very dense. The same reason they are also very dense, because these electrostatic forces are so strong that they bind together these like currently we have partial charges. In ionic compounds we have complete transfer of electrons, so we get very strong full charges. Unlike these partial dipoles, we have complete dipoles in ionic compounds. So the electrostatic forces over there are very strong. So if you're studying ionic forces, consider the fact that now you know electrostatics. That is why you understand ionic compounds a lot better than people who do not incorporate electrostatics with ionic compounds, right? So considering the fact, we have covered that what will happen to the neutral glass. We were discussing that if there is a positively charged glass and there is neutral, now we know what is going to happen. Dipoles are going to get constructed, or you can say being induced. So if this is positive, it would become negative, and eventually they would get attracted to each other, and hence when they will come closer to each other, this is what we're going to see. This pull will be generated, right? We're going to see them getting pulled to each other, right? This is a very basic phenomenon. This was self-assessment from topic 13.1. I hope I was able to explain things for you in a much easier manner. Now all you have to do is to just read this topic 13.1 as a whole. Please read it again if you're not clear about any fact or any statement. If you need my help, you can leave a comment for me in a chat box on MS Teams, and I'm going to try to respond to you as soon as possible, or you can leave me a personal message on Teams so that I may be able to respond to you later. Then we're going to discuss topic 13.2 in our later video. I hope I'm going to cover this chapter soon enough, because it's a very long chapter, and I think a lot of details is needed just to make you able to understand the chapters ahead, since this is the very basic understanding of both current and electricity, as well as electromagnetism. Everything starts from actually electrostatics. This is the very beginning of the whole charged particle game, right? And thank you for watching this video, and please leave your comments on MS Teams for me, so that I can see what else you want to know and how we can deal with your academic issues, right? Thank you.